4.5 Lesson 2 Derivatives of Inverse Trigonometric Functions. Our objectives are 1. You will know that the trigonometric functions are not one-to-one, but their domains can be restricted to make them one-to-one so that they will have inverse functions on their restricted domains. We saw this yesterday with the sine function. We restricted the domain of the sine function from negative pi over 2 to positive pi over 2. On that restricted domain, the sine function is one-to-one and therefore has an inverse sine function. You will be able to prove some of the differentiation rules for inverse trig functions. Today we'll take a look at proving the differentiation rule for the inverse tangent function. Yesterday we looked at proving the differentiation rule for the inverse sine function. And using the differentiation rules for the inverse trig functions, you will be able to find derivatives of inverse trig functions. So for the cosine function, you can see that here we have the graph of y is equal to cosine of x, and the graph fails the horizontal line test. The function is not one-to-one. However, we can restrict the domain of the cosine function so that we're only considering the cosine function on the interval from x is equal to 0 to pi, and on that restricted domain, the cosine function attains all of its output values from negative 1 to positive 1, and the cosine function is one-to-one on that restricted domain. So on that restricted domain, it is possible for us to define the inverse cosine function, and that's what we have here. Y is equal to the inverse cosine of x if and only if y is the angle between 0 and pi, such that cosine of y is equal to x. Y is equal to the inverse tangent of x if and only if tangent of y is equal to x, where y is coming from the interval from negative pi over 2 to positive pi over 2, not including the endpoints. And again, why do we have to restrict the domain of the parent tangent function? Because the tangent function is not one-to-one. But if you restrict the domain of the tangent function so that we're only considering the interval from negative pi over 2 to positive pi over 2, not including the endpoints, on that restricted domain, the tangent function attains all of its output values from negative infinity to positive infinity, and on the restricted domain, the tangent function is one-to-one, so we can define the inverse tangent function. So the inverse tangent function is defined as follows. So y is equal to the inverse tangent of x if and only if y is the angle between negative pi over 2 and positive pi over 2, such that tangent of y is equal to x. Here we have the graph of the cotangent function, and you can see that the graph of the cotangent function fails the horizontal line test. The cotangent function is not one-to-one. Therefore, it does not have an inverse function unless you restrict the domain of the cotangent function from 0 to pi. Then on the restricted domain, the cotangent function will be one-to-one and therefore have an inverse function. And we define y is equal to the inverse cotangent of x as follows. So y is equal to the inverse cotangent of x if and only if cotangent of the angle y between 0 and pi over 2, between 0 and pi is equal to x. So here we're looking at the graph of y is equal to secant of x. This is the domain of the secant function. Actually, this is the restricted domain of the secant function on which the secant function is one-to-one. So the domain of the secant function is all real numbers except those that would make cosine equal to 0. because secant is 1 over cosine. So any value of x that would make the denominator cosine equal to 0 must be excluded. But on that domain, the secant function is not 1 to 1. But if you restrict the domain as we see here, or alternatively, in a different way, as we have in our textbook, then the secant function becomes 1 to 1 on the restricted domain. And we may define the inverse secant function as follows. Y is equal to the inverse secant of x if and only if secant of the angle y is equal to x, where the angle y is coming from the restricted domain of the secant function. And the same is true for the cosecant function. The domain of the cosecant function is all real numbers except those that make the denominator of 1 over sine of x equal to 0. Because remember, cosecant of x is equal to 1 over sine of x. So the domain of the cosecant function is all x except those that make sine equal to 0. However, on that domain, the secant function is not 1 to 1, so you have to restrict the domain to make the secant function 1 to 1 so that we can define an inverse. And there are different ways you can do that. In our textbook, we do it as follows here, which is what you have here, from negative pi over 2 to positive pi over 2, but not equal to 0. So on that restricted domain, the secant function is 1 to 1, and therefore we may define the inverse secant function as follows. Y is equal to the inverse, not secant, but y is equal to the inverse cosecant of x, if and only if cosecant of the angle y, where y is from this interval, not equal to 0, is equal to x. So we looked at objective 1. We saw that the inverse trigonometric functions are not 1 to 1, but their domains can be restricted to make them 1 to 1 so that they will have inverse functions on their restricted domains. And now we will take a look at proving the differentiation rule for the inverse tangent function. And then we'll look at 4 examples for using the different differentiation rules for the inverse trig functions to find derivatives of inverse trig functions. So we'd like to prove that the derivative of the inverse tangent function is equal to 1 over 1 plus x squared. So how do we do that? To prove that the derivative of the inverse tangent function is 1 over 1 plus x squared, we have to begin with the definition of the inverse tangent function. So we start by writing y is equal to the inverse tangent of x, and our objective is to find the derivative, or y prime. You can also write dy dx. That's another way of representing the derivative of y with respect to x. So these are alternate notations for the derivative. And that's what we're after. We want to show that y prime is equal to 1 over 1 plus x squared. So our first step in doing that is to use the definition of the inverse tangent function. Y is equal to the inverse tangent of x if and only if y is the angle between negative pi over 2 and positive pi over 2 such that tangent of y is equal to x. So we may write, this implies that tangent of y is equal to x. how do we find y prime? We did the first step, which is to rewrite the inverse tangent function using its definition as tangent of y is equal to x. And we're after y prime, and what you have to see here is that on the left side of this equation, you have tangent of y, and you're going to see that as a composition of two functions where the outside function is tangent and the inside function is y. Because we're going to be differentiating with respect to x to find dy dx, or y prime. So we have the derivative with respect to x of tangent of y is equal to the derivative with respect to x of the right side of the equation, x. So on the right side of the equation, the derivative with respect to x of x is just 1. On the left side of the equation, you're differentiating with respect to x, but the inside function is y, so we treat that as a differentiable function of x, and we have a composition of the outside function tangent and the inside function y, where y is some function of x. In our particular case, it is, of course, the inverse tangent of x. So the derivative of tangent is secant squared, so we have secant squared y, and then you multiply using the chain rule by the derivative with respect to x of the inside function y, which is what we're after. It's dy dx, or y prime. And we got that using the chain rule. So the next thing that we have to do is we have to isolate what we want. What we want is the derivative of our function. We want y prime, so we will isolate y prime to get the derivative of the inverse tangent function. So we have y prime is equal to 1 over secant squared y. We want our derivative to be in terms of x. Currently, we've isolated the derivative, but it is in terms of y. So how do we go from what we have to what we want? We will use what we know about the inverse tangent function. We know that by definition it is the angle y between negative pi over 2 and positive pi over 2, such that tangent of y is equal to x. And we're going to draw a right triangle to help us, so we can write x as x over 1, and we can draw this right triangle. So we have the angle y, and from right triangle trigonometry, we know that the tangent of y is equal to the ratio of the length of the opposite side to the length of the adjacent side. And here's the angle y. So the length of the opposite side is x, and the length of the adjacent side is 1. So now we will find the length of the hypotenuse of this right triangle using the Pythagorean theorem, so that we may use this right triangle and replace secant of y with an expression in terms of x. So using the Pythagorean theorem, we have c squared is equal to a squared plus b squared. So c is equal to the square root of 1 plus x squared. 1 squared is just 1. So we may replace c with the square root of 1 plus x squared. And what is secant of y? Secant is the reciprocal of cosine. So if cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent. So secant of y is, looking at the right triangle, it is the ratio of the length of the hypotenuse to the length of the adjacent side. So secant of y is the square root of 1 plus x squared, but of course what we have in the denominator here is not secant of y, but the square of secant of y. So that would give us 1 over, and secant of y is the square root of 1 plus x squared, but now we have to square it because we have secant squared y, and that gives us y prime is equal to 1 over 1 plus x squared. And of course, by now we have completed our proof, because we were trying to prove that the derivative of the tangent function is, the derivative of the inverse tangent function is 1 over 1 plus x squared. The derivative with respect to x of the inverse tangent of x is equal to 1 over 1 plus x squared. So we took a look at proving one of the differentiation rules for the inverse trig functions, and now we'll look at 4 examples for finding derivatives of inverse trig functions using the differentiation rules for the inverse trig functions. So these are the derivatives of the 6 inverse trigonometric functions, and we will use them along with the chain rule to find the derivatives of the functions that we will be looking at for the lesson today. So we begin with our first example. We want to find the derivative of the function y is equal to the inverse sine of e to the 2x. And what you have to begin with is understanding that what you have here is a composition of 3 functions, where the outside function is the inverse sine function, the middle function is the function e to the x, and the inside function is 2 times x. And we are, of course, taking the inverse sine of e to the 2x. So we begin by seeing e to the 2x as our inverse function for the... We begin by seeing e to the 2x as the inside function, where the outside function is the inverse sine function. So to find the derivative, you use the chain rule, because we have a composition of functions here. And you begin by taking the derivative of the outside function evaluated at the inside function of e to the 2x. And of course, what is the derivative of the inverse sine function? We have it right here. So we're going to write 1 over the square root of 1 minus, again, using the chain rule, we have to evaluate the derivative of the outside function at the inside function, which means where you see x in the differentiation rule, you're going to replace the x with whatever your inside function is. So you'll have e to the 2x squared. But that's not all. You have to use the chain rule further by multiplying by the derivative with respect to x of the inside function. So now to continue to find this derivative, you need to use the chain rule again, because you have a composition of 2 functions where the outside function is e to the x and the inside function is 2x. The derivative of e to the 2x with respect to x would be e to the 2x multiplied by the derivative of 2x, which is 2. So that gives you 2 times e to the 2x, and you can multiply what we have here by 2 times e to the 2x, which would make the numerator 1 times 2 times e to the 2x, which is 2 times e to the 2x. And in the denominator we have the square root of 1 minus e to the 2x squared. So you have the power of a power. So multiply the exponents and you get e to the 4x. And that would be our final answer. In number 2, we have the inverse tangent function, and then we're squaring the inverse tangent function. So we have a composition of 2 functions for number 2. But how does it differ from the composition that we saw with number 1? The difference is this. In number 1, in our composition, the outside function was an inverse trig function, and then we had an inside function. which itself was a composition of two functions. But the main thing is the outside function in our composition was an inverse trig function. In number 2, we have a composition. One of the functions is an inverse trig function. And however, the difference between 1 and 2 is that in number 2, the outside function is a power function, and the inside function is an inverse trig function. So we will be using the chain rule, but in number 2, it is the inside function that is an inverse trig function. So let's see how that turns out. So for number 2, you will begin by using the chain rule. So now you have to begin by taking the derivative of the outside function, which is a power function, evaluated at the inside function, which is an inverse trig function. So using the power rule, you would bring the exponent to the front, and you will have 2 times the inverse tangent of x raised to the first power, and you don't have to write the exponent of 1. And then you have to use the chain rule and multiply by the derivative of the inside function, which is, of course, the inverse trig function. And what is the derivative of the inverse trig function? It's right here. So we're going to write y prime is equal to 2 times the inverse tangent of x times 1 over 1 plus x squared. And when you multiply, you will get this as your final answer. Number 3, we have y is equal to the inverse cotangent of natural log of x, and we want to find y prime. And again, you see that we have a composition of 2 functions. The outside function is an inverse trig function, and the inside function is natural log of x. So we use the chain rule. We begin by taking the derivative of the outside function evaluated at the inside function, and then we will have to multiply by the derivative with respect to x of the inside function. So what is the derivative of the outside function? So we're looking at the outside function being the inverse cotangent function. So the derivative of that is negative 1 over 1 plus the square of the inside function. So now we have negative 1 over 1 plus, and again, using the chain rule, we have to evaluate the derivative of the outside function at the inside function, which of course for us is natural log of x. So we have negative 1 over 1 plus the square of natural log of x. Which I can write this way. And then we have to multiply, using the chain rule, by the derivative with respect to x of the inside function, natural log of x. The derivative of natural log of x with respect to x is 1 over the argument. It is 1 over x. So our next line will be y prime is equal to negative 1 over, this derivative is 1 over x, so I will replace that with 1 over x. And of course you have to multiply these two fractions. So if you want to simplify, you can write the final answer as x times, in the denominator you will have x times 1 plus the square of the natural log of x. So our last example is y is equal to the inverse secant of x over 5. We have a composition of 2 functions where the inside function is x over 5 and the outside function is the inverse secant function. So we're going to be using our differentiation rule for the inverse secant function. and we will begin by taking the derivative of the outside function, but we have to evaluate it at the inside function using the chain rule, and then multiply by the derivative of the inside function. So we will have y prime is equal to, using this differentiation rule, we have 1 over the absolute value of the inside function times the square root of the square of the inside function minus 1, and don't forget, now you have to multiply by the derivative of the inside function because we're using the chain rule. So you have the derivative with respect to x of x over 5, which you can write as 1/5 times x. That's just another way of writing x over 5. So when you differentiate that, you get 1/5. So you can write y prime is equal to 1 over, you have the absolute value of x over 5. Well, x over 5 is 1/5 times x. 1/5 is already a positive number, so you can take it out of the absolute value, and then you have the absolute value of x. And then you have the square root of x squared over 5 squared, which is x squared over 25. And then you can write 1 as 25 over 25, allowing you to write your radical expression as I've done here. And this derivative is, of course, 1/5. And then you're able to cancel this derivative, the 1/5, with the 1/5 in the denominator, giving you y prime is equal to 1 over the absolute value of x over the square root of x squared minus 25 over the square root of 25, which is, of course, 5. So now, in the denominator here, you can just multiply the absolute value of x by the square root of x squared minus 25 over 5, and it will become the absolute value of x times the square root of x squared minus 25 over 5. And then your final answer, you're dividing 1 by what you have here that I circled in gold. So you multiply by the reciprocal, and that would just result in the final answer of 5 over the absolute value of x times the square root of x minus the square root of x squared minus 25. That is the derivative of our function y is equal to the inverse secant of x over 5. So we just saw some examples of finding derivatives of inverse trig functions using the differentiation rules for inverse trig functions.